This is our third recitation. And today we will talk about electric potential. The electric potential. From mechanics, we know that if a force is conservative, force is a conservative force, then there is potential energy function U such as integral F dot dr from R1 to R2 is equal to minus change in potential energy function U at R2 minus U at R1. U is a potential energy function that exists for conservative forces. If I divide both sides of this equation by a test charge Q naught, 1 over Q naught is integral from R1 to R2 F dot dr minus, I divide both sides by 1 over Q naught. Q naught is a test charge. By definition, test charge is positive. Then what we have on the left-hand side of the equation is force divided by Q naught. I remind you that by definition of electric field, the way we introduced it, electric field is limit with Q naught to 0, F divided by Q naught. So on the left-hand side of this equation, F divided by Q naught, I have integral from R1 to R2 E dot dr. And on the right-hand side of this equation, I have minus and difference in potential energy function divided by Q naught by definition is difference in electric potential. V is the electric potential. V at R2 minus V at R1. So integral from R1 to R2 E dot dr is equal to minus difference in electric potential. From mechanics, we also know that if a potential function U exists, then from this scalar potential energy function, we can retrieve both components of force. So what will be Fx? It is partial derivative minus partial derivative du dx. And Fy is minus partial derivative du dy. If I write it in polar coordinates, then I will get Fr, radial component of force, is minus du dr, and tangential component of force, F theta, is minus partial derivative du r d theta. Now instead of force we have electric field, and instead of potential energy function we have electric potential. So I will write both components of electric field both in Cartesian and in polar coordinates. So what is ER? ER will be minus dV dr. This is in polar coordinates. And then E theta will be minus dV r d theta. And in Cartesian coordinates, I will get Ex is minus dV dx. And Ey is equal to minus dV dy. Now we have all formulas that we need to solve problems on electric potential. So now I will summarize the formulas that we will need to solve problems on electric potential, on the electric potential. What are these formulas? Integral from R1 to R2, E dot dr, is equal to minus difference in electric potential V at R2 minus V at R1. I remind you that electric potential is a scalar. We need more formulas. We know that if we know this scalar V, it's very powerful that from this scalar we can retrieve both components of electric field. So I have Ex, that is minus dV dx. I have Ey, that is minus dV dy. And if I write it in polar coordinates, I have a radial component of electric field, dV dr minus dV dr, and E theta is minus dV r d theta. So the first problem that we will solve, we will find electric potential created by a point charge at the origin. So this is problem 1, and it will be electric potential created by a point charge at the origin. So this is the origin. We put a point charge here, let's call it Q, and I want to find electric potential at arbitrary point X and Y. This is X and this is Y. We know electric field created by point charge. What is the electric field created by point charge? It is coefficient K, 1 over 4 pi epsilon naught, and then I have point charge Q divided by R squared, and it is radially out or radially in depending on the sign of this charge. So this is radial component of electric field created by point charge. I will write it in components. ER, radial component. ER is K Q over R squared. We know that ER is this expression, E theta is 0. So this is one-dimensional problem. I can write ER, I use this formula. I can write it as minus straight derivative minus dV dr. And if I have this, then what is V? Let me think. I will probably write it here at the top. So V will be minus comes here, minus integral ER dr. Okay, now it is minus integral ER is K Q over R squared dr minus KQ are constants, KQ, let me write it again, minus KQ is a constant, and integral dr over R squared is minus 1 over R. Minus and minus plus. So I have KQ over R. This is indefinite integral. So I need to add constant plus constant. If I want electric potential to be 0 at infinity, so R tends to infinity, then I want electric potential be 0. Then my constant is 0. And electric potential created by point charge V at any point R is equal to K, point charge at the origin, divided by R, where R distance from the origin to the point we are interested in. We found electric potential created by point charge that we will use a lot in our problems.